there are ways I have ways to show the information on my screen. So maybe we can try, I don't know, something. Maybe let me spotlight myself. That probably is easier. Oh, I spotlight myself already. Okay. Uh, maybe if you do you see me or no? Yeah,
Yeah.
okay. So if you I guess, let's just do some practice while waiting for your friends. Uh, okay, so on a scale 1 to 10, 1 being not ready, 10 being overly prepared, please use your chat box to show how ready you are for exam 2. Okay, I like this group. So this is way better than I thought. It will be a fast review session then if you guys are ready. And if you have question, you can raise your hands. I don't know, maybe you guys already forget how to do Zoom. It has been a while since I play with Zoom. So far, no one raised your hands. So maybe let's play another game. Maybe you can use your chat box to say where you're from. I see there are people from Dallas, New York, Chicago. Brooklyn is from Chicago. Cool. We will basically keep on doing this until you guys ask questions because I'm not gonna go through lecture
Uh,
9, 10, 11. Okay, good.
I have a question. I don't know how to raise
Good.
my hand in the I had some it was on the like the spring practice quiz. It's
Okay.
using it's calculating like EMF in a circuit through Kirchhoff's like right loop and stuff like that. It's having a circuit with like known resistors and EMF areas but needing to calculate for the EMF of one of them or something like that. I just find that I go through the calculations incorrectly, and I was wondering if we could work through one, potentially even the one that was on the spring practice exam, or if
Spring practice exam. Okay, so let's do that. But first, I need who wants to volunteer to be a co-host? Matthew, do you want to volunteer?
I'm sure I don't know exactly what a co-host is, but sure,
Meaning like
yeah.
there are so many students entering, you just need to click admit because
Oh, okay.
otherwise I will not be able to move my mouse. Let me Matthew Collins
Yeah.
at
And that'll just
co-host.
be in the participants area.
Yeah, participant. And then maybe Darshan if you want to be co-host. Then I don't have to worry about admitting people. Okay, so let's go to this practice quiz. Um, Practice quiz. My, where is my win? Where is my Chrome? This is my Chrome. Okay, good. So
so like practice like question 6 and 7 would be good ones, but mainly 7.
this one. Okay. Maybe if it's too small. Okay. Yeah, this is from homework, right? Uh, so we have this is taken straight from the homework, I think. From the circuit shown above, assume that the EMF is this number and R, which is here, is 5.6. Okay. Find the EMF E1 in the circuit. Okay, good. So Braden, how do you approach this problem?
I believe that you have to start you have to use the right, you have to like identify each loop and then through that by isolating a variable, get it.
Okay, so maybe there is this maybe there is a way to use my annotate screen. So first, okay, so first I would use this loop if I were you. You can use other loops, but this one is the most straightforward because the current here, the current along this path or this branch is known, but the current along this branch is unknown, right? So you still need to find the other current. Let's call that I3. So first you need to do that. Then I3 is equal to 1 amp because you can use the junction rule along this node. So
Are
1
you
amp.
drawing this somewhere?
Oh,
Sorry.
you cannot see it? Okay, sorry. Maybe
No, no, no.
this one will make it
Yes, I
better.
can see it
Okay.
now. Yeah, thank you.
No, sorry, I apologize. It was my Chrome, now it's my whole screen. Okay, first let's repeat. Okay. I'm gonna repeat. So if I were you, I would use the top loop. This is because there are only two unknowns. In terms of electrical components, there is only one unknown because we know R and we know R is this, right? And we know EMF, which is 22.5. Okay. But there is another thing that you don't know. So we need to find that first. Let's finish what we know. We also know the current along this branch from this node to this node is known, which is 1 amp, right? But the current from the same node to the other same node is unknown. So you need to find that first. You find that by using Kirchhoff's junction rule. So you have I and for this, I don't have preferred direction. You kind of know what's the number, what's the direction that gives you positive number, which is into the node, into the junction. So there is unknown current here, known current in, and known current out. The answer is, without doing it explicitly on the screen, is 1 amp. Is that clear? Is that clear or no?
Yeah, yeah, that makes
Good.
sense.
So you get 1 amp. If people if it's not clear, you need to let me know. Okay. And then what else? Okay, so now you know the currents. Then you can use a loop rule for the top loop to find this one. Right? Are you good with that, or I know you can do it?
Can you explain the math for that again?
Okay. The math or the concepts?
I would say the math because I understand the concepts, but I don't
Okay,
know
good.
the
So
math to
let
get
me
there.
how to do that, because I'm using my screen right now. I'm switching to my iPad. Anyway, I can switch my iPad now. My iPad stops working. Oh, create. Okay, so oh, interesting. Okay, good. So let's put the question here and make it so, or maybe I should redraw the circuit. So the circuit it looks like this: resistor, 1 amp, This one is 22.5. Okay. And then this R here is 5.6. So I will need your help to put the number because the number is not going to be nice, I think. And this is unknown, right? And then this one is 1 ohm. And during the exam, I recommend you to draw the circuit. That's how to do physics. You make a lot of drawings. Okay. And then for the current, let me make it a little bit thinner. For the current is basically 1 amp, but we need to worry about the direct. We need to care about the direction. Okay. So we know that and then we can use, let's just do clockwise. Okay. So for the okay, the reason why I'm not drawing the bottom loop, because at this point we have enough information. What I mean by enough information is that we can generate one equation for one unknown. Okay. So we can have, plus unknown EMF minus 1 amp times 1 ohm. Okay. Sorry, I need to make sure you know the direction. So the direction of the loop is like this. So first, the loop hits negative pole and then positive pole. So we have plus, and then the current, this 1 amp, is in the same direction as the loop. So it's negative. And then there is another negative here, which is 1 amp times 4 ohm. And then the current right now is the opposite, meaning what I say right now is here. It's the opposite of the direction of the loop. Okay.
And so in that case, you add it.
Yeah, we add, good job. Okay, so this one is 1 amp times 1 ohm. So this one just cross. And then the voltage will be negative because it's the opposite. So because the loop hits the positive pole first, then the negative. So minus 22.5 volts. And then the current, and then this one becomes positive 1 amp times 5.6 ohm. If you want to make, and then this, everything is equal to 0, right? And then if you want to make it tidy, don't do this for all numbers. But if you see 1 is basically kind of useless information. The unit is important, but if you want to make it easier to see, you can cross that. But let's not do that for now. So basically 0 is equal to the unknown minus 4, basically volt, minus 22.5 volts plus 5.6 volt. The reason why I can just use volt because amp times ohm is volt. So it's basically 22.5 plus 1.6. And then there is a negative sign. Interesting. Sorry. This one is negative. So it's 22.5 plus 1.6. I thought that this was positive, but the correct sign is negative. So basically, yeah, you can do the math. Yeah, 22.5. Anyway, the answer is 20.9. Is that right? If you put it in your calculator.
Yeah,
Because
that's
the
what
only
I thought.
number that makes sense is this one, is this one here, right?
And
Um,
even though the answer that we get out of it is negative, we take the
sorry,
absolute.
it's actually positive, Braden.
Oh, okay.
Yeah. So the reason why, okay, so what is this? 20.9 volts is equal to 0. So the number, you can move that to left-hand side, so it becomes positive.
Okay, yeah, I
Okay.
see. Okay, thanks.
Yeah, if you see similar problems, typically it's better to put the signs. So instead of having two options that have positive and negative, typically I just ask the magnitude. And then if I care about the sign, then if you get the magnitude correct, you get half of the point. There is a way to do that on Canvas. Good. Okay. Any other question?
So I think one
Oh,
thing,
second, I think what? Somebody said something. Brooklyn, still raising your hand. Are you still having question?
Yeah, so I actually had a question about question number 6 on the practice quiz about how to do the loop rule.
So let's do practice quiz. Practice quiz again. Okay, you guys.
before we do that, could I ask just a clarification question on this real quick? Sorry, my
Yeah.
audio was like glitching. So I think one thing that I've been confused about was like where the current in a circuit changes. So like I was thinking like every time in like a series of parallel circuit that a current goes through a resistor, that current value changes. But is that like just with like the junctions in Kirchhoff's rule? So like current will change at a junction and nowhere else? Does that make sense?
Okay, so maybe so the current change when it encounter a change. Okay, so one is if there is a resistor, current change. If it goes through a wire, it doesn't change. Wire is basically infinite. You can imagine wire, or you can make the analog of a wire as a channel with infinite width. Basically, it doesn't affect the currents. Back to your question. Can you please repeat your question again, Darshan?
Yeah, so so current if current changes when it goes through a resistor, does it also so obviously like at junction points, the current that's a place where like the current well I guess like at a junction you have three different wires, so the current
Yeah.
wire could be different.
Okay.
But like is that like the only time where a current changes in addition to like resistors or
So maybe so maybe the simplest circuit is something like this, right? So as long as the current is on a wire, then the current doesn't change. But once sorry, I was talking about a voltage. So here in a loop, sorry, I was talking about the voltage. I apologize. Thank you for being so patient with me. You should just say wrong. Uh, okay, so in this loop, the current is the same. But I guess the question, Darshan question is what happened if we have another loop, right? So yeah, so between two nodes, the current is the same. So the current is the same from this part of the wire through the battery and this node. So that's one. This one also the same. Another one is this one. So there are three currents in this example. Okay.
I see. So the current doesn't like the obviously at the junctions you're probably going to have different current values for all three wires in a junction, but for each of those loops, the current remains the same throughout the loop.
Yeah. So there is another thing that I think I asked this only once in the past, uh, which I may ask tomorrow. We'll see. I haven't finished the exam. I had a grant due this morning and and another draft due today that I already postponed until after the exam. So one can put this. The name is jump wire. So if somebody, can you see the green wire? There is no component in it. So this green wire provides zero resistance. So for physics 112, then, okay, first we cannot have something like this. There's need to be a resistor somewhere. But the current will just go, all the current goes through the jump wire. Because this one is like no resistance. If this current, the other alternative has non-zero resistance. So if there is a wire that doesn't have any components, then all currents go to this direction. The name is jump wire if you do electronics. The reason why I didn't put the resistor here because you know from the lecture slides that there is internal resistance, which is small r. But to make it easy to our eyes, I added this resistor here. Okay. Does it help, Darshan?
It does. This makes a lot more sense. Thanks so much for clarifying.
Okay. Brooklyn, do you still want to ask your question, or Katie, do you want to ask your question? And
Yeah, so
Christine is Katie first, and then Christine.
Yeah, so I still wanted to know about question number 6, just how to do the loop rule, because I understand like the directions which determine whether or not like each component is going to be like positive or negative, but I don't know how to put together the equation.
Question number 6. Can you remind me question number 6 of what? The practice exam?
Yeah, on the practice exam.
Practice exam again. Okay, so this one, number 6 or number 7?
Number 6.
Number 6. Okay. This is taken straight from the lecture notes, I think. Maybe. So so the question is, which one of the following is the correct loop rule for the right loop? First, loop rule, so not junction rule, for the right loop. And somehow I provide the direction. Okay, so let's see if I can annotate this. Annotate screen. So because this is okay, first maybe anyone wants to answer this question?
Yeah, I can try.
Who is this?
Katie.
Wait. So who asked the question? Katie asked the question, and you want to answer it yourself?
No. Brooklyn answered the question or asked the question.
Brooklyn asked the question. I apologize. I'm sorry, Brooklyn. There are so many windows here. Okay, so yeah. So what is the answer?
Yeah, so for these types of problems, basically, the answer that I got was A. And I kind of you just kind of pick a point to start. So my starting point usually is the batteries, but because this problem starts with the first current and first resistor, that's where I chose to start.
Yeah.
So the direction is already given to us. So if we go in the direction, we see that the current and the loop are going in the same direction, which means they're going to be negative. So it'll be negative I1 R1, which is like all of them. So that tells us nothing.
Well, all of them except D.
Yeah. So it just tells us that D is not the answer. And then you get to the first battery, which is V1, and you hit the
Yeah.
negative terminal first. Sorry, there's like a fly.
Yeah.
So it's positive because you're hitting the negative terminal first, which
Yeah.
also tells us that D is not the answer. And then you get to you turn and the current changes. I guess I shouldn't say the current changes, but I2 goes in a different direction.
Yeah.
So because we hit I2 like head on, it's positive. So I2, R2 should be plus, which tells us that A is the right answer.
Okay, good. So using your chat box, who thinks that who thinks is you can enter your answer A, B, C, or D? So I think your friends thinks that your answer is correct, Katie. So good. Okay. Is there anything else? I mean, meaning like anything that Katie missed? Yeah, I have nothing to add really. I think Katie did a good job. Okay. So next, I think Christine asked a question before you, Katie. So Christine, do you want to ask? Do you want to share your question with the class?
On the study guide with the answer sheet, slide 40.
Slide 40. Slide 40. Slide 40. With the answer sheet. Okay. Slide 40. Slide 40. Oh, this problem is kind of difficult. The exam will not be this involved. But let's go to slide 40. 40. Oh, okay. Good. People can see the question, right? Sorry. Rectangle. Basically, this is a DC motor. A question about DC motor. Let me read the question because typically I answer without reading the question. A rectangular coil with corner label A, B, C, D has length. And maybe if you want to enter your answer, you can, for just for the fun of it. So there is a dimension, length, and W. I need to make it a small letter next time. It is placed between the poles of a magnet. So there is a magnetic field like this. If a current I flows through this coil in the, I know the answer of this question, by the way, because the question is force. The torque is trickier. If a current I flows through this coil in the direction shown, what is the direction of force acting on section A? Oh, not the, see, this is why I need to read the question. This is not like the total force, but a force along only one part of the motor, okay? So maybe some of you answer. Let's see. Wait, is this the answer from last time? Maybe. Okay, let's see. Maybe not. Maybe both answers are A. So we know that the field goes from, let me switch to red, from left to right. And then the currents goes up. Maybe goes up because of the polarity of the battery. Okay, so we know that they are perpendicular with respect to each other. That means the force is going to be non-zero, right? So on the exam, I may say, you know, what are the conditions for such that this charged particle doesn't experience a force? Maybe one of the answers could be parallel. Okay, I'm just trying to let you know that parallel is the opposite of perpendicular. Okay, so the current goes up. Current is my pointing finger. Magnetic field points to the right. So the force point into the page. So the answer is A. Good job. So I think all of you got it right. The answer already disappeared. So Christine, was that clear?
Yes, thank you.
Okay. Let's see the answer. Okay, the answer is A. Ah, I hope all of you did it together with me instead of opening the next page. But the answer is A. Okay. Any other question?
So just to clarify again,
Yeah.
so this like version of the right hand rule is for if you have a particle of magnetic field direction and a force like we just had. Whereas this is for like the solenoid ring loop kind of
Yeah.
thing.
Yeah.
Okay.
Yeah. So this one is for ring. There could be another one that use this curling motion. It's so this right hand rule and this curling motion is a common operation in math. So when I say the other, there could be another one is only for this class. But in physics there are many examples that use right hand rules. The name of the operation is cross product. You don't need to know what that is. Okay.
Okay.
Any other question?
Sorry, I just had a question on when I'm doing the right hand rule with that and like the magnetic field is pointing right and my index is pointing, oh wait, yeah, my index is pointing up.
Yeah. You need to. I mean, I didn't flip the screen, but my right now my middle finger is pointing to my right. Yeah. Okay. And then
But then it points to my middle finger is pointing to me for some reason. I don't know why.
wait, your middle finger pointing to you?
Yeah,
Sorry.
because isn't my thumb supposed to be going to the right?
Wait. Which question is this? Or
The one
any?
we just did, the one about like the current going up, magnetic fields.
Okay, good. So maybe we need. Sorry. Maybe we need to go through this again. So magnetic field points to. Okay, so I don't want to use my left hand rule just because of the camera. But just trust me that I'm using my right hand rule and
Okay.
I'm putting it. I'm basically so I made a mistake in my class because I solved it using whiteboard, and when I pick the answer, I use the same direction and use my basically my iPad. But right now I'm using just my iPad. So my middle finger points to the right, okay,
Okay.
and then I keep the same shape.
Oh, okay. Sorry, I got it.
Yeah, and then basically my in the end my thumb points down and my iPad is on my desk. So the thumb points into the page.
Okay, thank you.
Got it. Okay, good. Any so who asked question? I think Matthew, you asked a question, right?
I have a question, but we can wait until Katie gets hers first.
Oh, Katie hasn't asked question. Okay, her question. Okay,
Thank you.
Katie.
Sorry. I wanted to go to question 11 on the practice exam or exam 2 from 2023.
Okay,
This is another right
so
hand rule.
question what? Sorry.
11.
Good. This one you have to be careful. The sign of the particle is negative.
Okay, so it would be the opposite of whatever the right-hand rule
Yes.
comes out to be. Okay.
Yeah. Do we want to do this as a class right now or no?
Yeah, can we just do it really quick? I just want to make sure that I'm
Yeah,
doing it
okay.
correctly. Sorry.
So again, use the chat box. And there is a question by Suraj. Can you please clarify again why this one Suraj, if you still have question about this problem, we can chat after this review session. Okay.
No worries. Christine was kind enough to answer it in the chat.
Okay. Good. Sorry.
Appreciate it.
Again, there are so many boxes here. And if I miss your questions, just unmute. Okay. So I think we're still taking answer for this question. Maybe seems that most of you answer C. So typically that's right. So basically we use right hand rules, and then the velocity is my pointing finger to the left, and okay.
Yeah,
Good.
it's like
No.
12.
Sorry.
Yeah,
This
it's like
one,
two right
this
hand.
one is not part of exam 2. I apologize.
Okay.
Yeah, sorry. This is the other right hand rule that we haven't done. So basically, the current is the direction of your thumb, and then the magnetic field is the direction of the way your fingers wrap around. Yeah, this is part of exam 3. Sorry. And then be careful with the sign of the charge. Okay. Good. Katie, maybe next, Matthew.
Yeah, could we go over question 4 in the practice exam?
Question 4, practice exam. Camera 3. Okay, good. When the switch in figure above is closed, the reading of the ammeter A will. Okay. All right, so let's use. Maybe some of you already answered. Nobody. Okay. Let's annotate the screen. So when before the switch, then you have a circuit with two resistors in series. Is that clear, Matthew?
Yeah.
Okay, good. And then when the switch is closed, then we have 3 resistors. So resistor R is in series with a parallel arrangement of resistor R and R.
Yeah.
Okay.
And you should get a resistance drop once they close, because they're in parallel to each other.
Yeah, excellent. So
on
the
the
question
practice
is
exam, I said it stays the same because I was thinking loop rule amps are always the same in the same loop. But I don't know, is it that it increases to keep volts the same? Because when the resistance drops, the amps have to increase to keep a constant voltage.
Yeah, maybe let's do it. Sorry, my iPad is kind of slow. Maybe this one. Okay, so maybe let's do it together. Wait, what am I seeing here? Oh, here, and then here. Okay, so when the switch is closed, if anyone wants to answer this, you guys can do it. It's more fun if you guys are the one that teach each other. So this is open, I guess, open for open configuration, basically we have two resistors in series. Right? Because the currents cannot go to this part of the circuit. Can you see the inset?
I have a question about this actually.
Katie.
Is the implication in the question that the resistance is equal in all three resistors?
Oh, it's not implication, it's a given.
Okay. Okay.
Yeah.
Thank you.
Maybe it's not clear. Yeah. If it doesn't say R1, R2, R3, then it is what it is. They
Okay.
are identical. R. Okay. So if you want to do it systematically, then this one is equivalent to R, right? And you can use V or EMF. So this one is equivalent. So I is equal to, I just care about I because that's what the question is asking. The EMF divided by 2R. So we can call this IO or I open. Okay. And then for close, when the switch is closed, we have one resistor of R and then a parallel arrangement of two resistors. Each has resistance of R. Okay. Is that clear? Let me close. And then if you are fast, I think Matthew said that it decrease. Should be R divided by 2 here.
The exam, I put decreased and the exam marked that incorrect.
The voltage, I
Wait,
think,
give me a
should
second.
increase, but the resistance drops.
Okay, yeah, you're fast, so I'm slow. So let's do it. So this is something like this, right? Basically. I hope you guys can recognize it. So this one is equivalent to this single resistor here. Okay. And then you can further collapse the circuit into one resistor and one EMF. So R3 half or 1.5. Okay. And then the current for close is equal to EMF divided by 1.5 R. Okay. So that means the current increase. Is that what is that what your answer, Katie?
Yeah, that makes sense. So because the resistance drops, the current has to increase to keep the voltage
Yeah.
maintained. Okay, thank you.
Okay, good. Good questions. Let's see, is anyone raising hands? Katie?
Can we do the right-hand rule in question 12?
I was going to ask about that one as well.
Oh.
Thank you, Matthew.
You guys are
We're on
okay.
the same
Question
level.
12. Meaning you guys are highly motivated. Good. Sorry. Let me read the chat box in case there is any question. And then we can go to question 12. Okay. Okay, good. So now question 12. This is a good question. There will be similar questions like this. This is basically a mass spectrometry question. Okay. Doesn't make sense. Okay. So three particles having the same mass, good. Same horizontal velocity. Yeah, makes sense because typically we couple this device with a velocity or speed selector. Enter a region of a constant magnetic field. One particle has a charge Q, the other one has a charge minus Q, and the third particle is neutral. Okay, so from this, you can tell which trajectory is the neutral one. Sorry, where is my, yeah. So the neutral one is the middle one because it doesn't get affected by the magnetic field. Okay. The path of the particle are shown in the figure above. In which direction does the magnetic field point? Okay, so it has to be perpendicular from the from the from the velocity here. Otherwise, the force is zero. Some students prefer to think in terms of equation. Okay, good. Let me. Okay, so we know that R. Okay, maybe I can answer. So anyone wants to answer this question?
I have an idea.
Okay, good.
So if you rewrite the equations, if you set the centripetal force equal to the magnetic force, you can solve for the radius.
Good.
You can write R equals mv over qb. So anything with a bigger mass, or sorry, I guess anything with a bigger charge is going to have a smaller radius. So the -2q, I think, is the top one that curves, that has the smaller radius, I think.
Oh yeah. You should know that. Yeah. That's the first.
Yeah, and then
yeah.
so then the positive one goes downwards, which I think indicates that the magnetic field also goes downwards.
The positive one
Or
goes.
it gives you like the directions for the right hand rule.
Okay, so I don't see. I think only one person answered, or
So I think
nobody
it's,
answered. Okay, good. So
I'm not sure.
yeah. So you can derive R. I wouldn't memorize it, but you can memorize it. I don't memorize the formula. The derivation for R doesn't take that long. But basically using our intuition that the more charges, the more force that the force is higher for bigger charge. Okay. So this one is based on what Katie shared with us. This is the -2q. And then the bottom one is the +q. Okay. It's just how nature works. If you have more charges, magnets will apply stronger forces. Okay. So here that means you know the direction of the force. The force at this position is like this. And then, so this is force. If you want to answer. And then velocity is like this. Now the question is, what direction is the magnetic field? So let me do it. So force point down like this, and then V point to my right, and then the magnetic field points away from the screen. Out of the paper. That's the question. That's what I would answer. Okay. Yeah. Nobody. Okay. Good.
Do you mind going over that again? So was the velocity, so okay, so like with R equals QB, MV over QB, I understood that part. Were we saying then that because, so like that equation applies because if we increase the charge, then we decrease the radius and that increases the force. So that's how we know that the,
Yeah.
the force is greater because with greater charge. So how then do we know that the force goes downward?
Because this one is the one for positive charges. Sorry, I apologize. I wasn't being precise. Thank you for asking the question. So the force point down for plus Q. Okay. For negative Q, I guess, let me repeat again. It points down because the trajectories looks like this. The trajectories for the plus Q is like this. Oh, sorry. It's like this. So the force at this point should point down. If the force points up, then the trajectory will look like this. Right? So what I meant by the force was the force that the positive charge plus Q experience at that position. So this is because I prefer to use the positive charge. So I don't have to use my right hand rules and then remember to reverse or flip the sign later. That's basically how I had in mind that I forget to share with you. Okay.
Okay.
So force like this, and then this is the same. The speed points to the right, and then you can use your right hand rules. Okay.
Sorry, I just wanted to clarify one quick thing on this figure. So, when we're looking at the velocity, we're not looking at the velocity's trajectory like within the magnetic field, right? We're looking at what the trajectory of the particle would be before it enters the magnetic field for the right hand rule, and then the
Yeah.
force indicates where it twists.
Yeah. Right after and enter the magnetic field, the green rectangle, because who just asked question? That was a really good question.
Suraj.
Suraj, yeah. So sure, because Suraj, at this position, the force actually point to the left, and the velocity points down.
Right.
But the magnetic field still points the same direction.
Okay.
That's another thing that I try to maybe I oversimplify things, but the direction of the force and velocity changes along in the name is uniform circular motion. It changes all the time.
Right. Okay. So you're saying for the point you picked, the force is down. No, the velocity is down and the force is to the left.
Oh, for this one, yeah, the velocity point down.
Okay.
The centripetal force points to the left.
Okay. Okay, got
And
it.
this is the FB. Okay.
Cool. Okay, and then this way it's still out of the page.
Okay.
Okay.
Yeah.
Thanks.
Yeah, it stays the same.
Sure. Thank you.
So were we like just saying that because like the top loop curves more than the bottom loop, then that's how we know that that is the greater charge, and because that is going, or because that must be the negative charge, which is greater, then we
Yeah.
know that that's in opposition of
Yeah.
the force, so the force must be downward.
Yeah. Because if you're being pulled because a uniform, yeah, because it experiences more force. Maybe that's an easier way to view it. It being pulled more. So it must be the one with higher charge.
Okay.
So on the exam, I may recycle some problems, but typically I change the signs and the directions. So if you look similar problems like practice problems or I click a question, don't just answer based on your memory. Sorry to digress. Any other question?
By any chance, are we able to look at the mastering physics homeworks? Is that something you have
Mastering
access
physics.
to? I had a question on homework 4. It's the same
Well, let's
Kirchhoff's
maybe we
law.
can keep that thing last. Or
Okay.
maybe because that takes time to to upload or to access. I'm
Okay.
doing it right now. Any other any simpler question?
From practice exam, the same practice exam, question 8. It's the charging capacitors type question.
Practice exam. Practice exam question. This is practice exam.
Yeah,
This
sorry, the
one.
same file we were just on.
Okay. Sorry. Question what? Sorry.
8. Or we could go to the homework also, that's fine too.
This one is faster. Homework takes time to find the question. Okay. And then we will go to the homework if that's okay with you. So before since there are some questions here, maybe we can answer those questions. Sorry. Before the question goes, what do you call, like get buried by other comments. So question from Ben, is the exam still on lockdown browser? It is on lockdown browser. You can take it anywhere. I'll be in the lecture room, but you can take it anywhere. Oh, Kerry has answered. Okay, good. Let's return to this question. Question from Matthew. What is the question here?
So it's just asking which one of these will, I think, fully charge the capacitors slower.
Yeah. So basically, we can use math. Slower, that means slower charging means longer or bigger tau, time constant, which
And then
is
you
equal
just
to
use,
RC.
yeah, then you just use the tau equals RC equation,
Yeah.
and then whichever one has a larger tau is slower.
Yeah, if you want to
Okay.
use it mathematically. But if you
Okay.
use, yeah, but basically, the larger the capacitor, the larger the water tank, the longer it takes to fill that water tank. And
Yeah.
then for capacitor, if you put it in parallel, it's almost the same as doubling their area. So the answer is capacitors in parallel.
Okay.
Yeah.
And it's just different from
Given that the
resistors.
resistor,
Opposite of
given that,
resistors.
yeah, given that the resistor is constant,
Okay.
which typically, I keep it constant. I think this figure is taken straight from your book. It's not my style of making of figure. Takes a lot of work to color figures. People answer C. Good.
What you said conceptually makes sense. I was wondering like which equation I could use to like think about it. So would it be like tau equals RC? Would it be
Yeah.
like T over RC equals something else or
Oh, so time constant. Time constant is, yeah, the equation for charging. Let me switch to my. So forget about this. Okay. So charging means the Q. Okay.
right?
So it looks like this. X is time. The y-axis is Q. So 0 to Q max. So this one is Q max. So the equation should be something. So Q. Your textbook use small q for a time-dependent parameter. So small q as a function of t is equal to q max 1 minus e t divided by tau. So when t reach infinity, then this term will be 0 and q is q max, like this. Basically, so this is the equation that Darshan asked, but don't have to think that far, because the idea of time constant of an exponential function is how slow things approaches how slow the parameter approaches some maximum value, or how slow something exponential decay, how slow or fast. So the larger the time constant, the slower the process is, whether it increases up to a maximum value or it exponentially decays. And then here, the time constant here, which is tau, is equal to RC. And R is constant, so it's proportional to C. Okay. Is that clear?
Yeah, thank you.
Yes.
Nobody raised their hands. So maybe we can go to the homework. Is that good? No? Yes?
That would be good, yeah.
Okay. So maybe you can read while waiting. Let me open the homework. So to homework. You can see this. It's not a secret. Yeah, so this is how I sync your grades. So it's manual sync. This is why it takes, I do this probably once a week. So when I say it takes time, it does take time. Homework 4. Which problem, Braden?
I had a question on number 3.
This one. Okay, good. Let me make it. Good. Okay. All right. So problem 19.54. What is the number that you have? So every student has a different number. So basically there is a power here. 5 omega. So the power or the heat loss is about this watts. I don't know what number is this, but we can call it P. So this watt is, we can set it to equal P, equal to P. The battery analysis. Okay, good. What current does? Wait, what?
In the description below, it says 22.9 watts.
Okay, good.
If you just want to use that number, I don't know, it's probably not the exact number from the other one, but it'll work for the concept.
Good. So, okay, so how to approach this problem? The first question is the currents along this branch here. Okay, and then, so how to get the currents? That's a good question, actually. And we don't, and the problem doesn't give the other currents.
No. It just gives you what you're given.
Okay. Because from the power, we can easily get the currents. So the power is V times I, which is equal to I square times resistance. And then P is known, which is 22.9, and R is 5 ohm. So we get I along this resistor. The question is, if we want to do loop rule, we need I, which is unknown here. Okay, good. Then we can, and then next we can do loop rule, right? So basically I that we just calculated, which is 22.9, which is square root of 22.9 divided by 5 is the I here. Let me annotate my screen. Sorry. So I, maybe let's just use this direction here. I is equal to, I'm using my mouse to write, so it's going to be square root of P divided by R. Do you guys know this or no? This is from, let me just switch this. This is from P is equal to V times I, and V itself is equal to IR, so it's I square R, which is an equivalent to I is equal to square root P divided by R. Basically, you can calculate I for the middle branch. Is that good? And then the next, and then the other one is just you can just label it as I don't know, I2, let's say. And then you can pick the direction. So this one could be I2.
I think you're on the wrong screen.
Good. On the wrong. Yeah, thank you. Yeah, I2, which is the same as I2 here, same as I2 here. Then the only unknown, and then if you use loop rule, set it to equal to 0, then you only have one unknown. You should be able to solve for I2. Is that good, Braden, or no?
I think so. I'm gonna work through it and see if I
Okay,
get the
good.
right.
And then you can email me your answer, and then we can do it together. But basically, first you use I guess the new equation for this is P is equal to V times I. What I mean by new is other than Kirchhoff's laws. We have done P is equal to VI. And then you can either express V as I times R, or you can express R as V divided by I. Yeah. Then no, you can sorry, I is not V divided by I is V divided by R. Then let me just do it. Then let me just summarize it. And P is equal to VI or I square R, which what we did here. Or if we want to express I as a function of V, I is V divided by R, right? So this one is equal to V. And then after you figure out what I is, you can use loop rule to find the current. Okay. Any other question?
I have a question.
Yeah, good.
So,
Who is this?
if similar to that question that we just looked at, if I were to instead be asked what value is the nanometer reading, how would I go about solving that?
Sorry, let me.
Because I saw there was a circle with A on the last example.
Yeah. Maybe that's something that. Okay. So amp meter. Let me just this. So amp meter, which is here, is so meter basically is a unit, but in many contexts, meter is a measuring device. Amp meter is a device that measure the currents. So it measures the current from this part of the circuit. Basically, sorry, let me wait until, yeah. So it measures the currents that pass through the amp meter, okay, which is the same circuit that starts from this node to another node. So A is basically just what is the currents at this position. Does it help?
Yes, that helps.
Okay, good. It's already past 3, so I don't want to take too much of your time. I can stay for a few more minutes, or if you have many questions, I can stay longer. But I guess I can ask you a question. Who is ready for exam 2? You can type yes or me to the chat. Nobody? Oh, there are 2 of you. Sorry, I just delete that. 2 out of 33, 3 out of 33. That's not bad. Any final question about anything? I guess the question is, do you like this Zoom class or no? Because I prefer Zoom class. It's just when it's just pandemic can only last for so long, which is a good thing. That's actually when I got Teacher of the Year because I use Zoom, and then I had to return to the class, and that's when I bombed my lecture. But if you like Zoom call, then we can. The next time I travel, instead of posting a recording lecture, we can switch to Zoom. Anyway, I think Matthew has a question.
Shanthi did in the chat box.
Chat
They
box.
asked if we could go over slide 56 on the study guide.
Slides 56. Slide 56 on the study guide. Study guide. Slide 56. Give me a second. Oh my God. Okay, good. Okay. So there is this figure here. Basically, cosmic ray would continuously bombard Earth's surface if most of them were not deflected by Earth magnetic field. Good. We learned about this on Friday. Given that the Earth given the Earth is to an approximation, doesn't need this excellent here, a magnetic dipole, the intensity of cosmic rays bombarding its surface is greatest at, yeah, what is the answer here? So basically, yeah, go ahead.
I would say the poles because that's where it's least dense at the magnetic field. Magnetic fields are very dense at the equator, it looks like from this drawing.
Yeah. So anyone wants to give different answer? That's one way. Okay, good. So most of you answer A. Yeah, that's a good way to answer the question. That's how I would answer. That's how I would think to come to answer this problem. Okay. Anything else? Any other questions? So you guys are ready? Pretty much. Oh, Katie has. I guess this is the final question.
Yeah,
Katie.
sorry. I was thinking about the slide we were on about the current due to Earth's magnetic field. What direction does Earth's magnetic field point, and do we need to like have that memorized for the exam?
So it kind of, you should know. because I assume all of you have played with compass. If you go to a national park, for example, they sell compass. That's how my son, I think, purchased his first compass. So compass, the north pole of a compass always points towards the direction of the north. Basically, always points to North Pole, but actually North Pole is our South Pole. So Katie asked in the context of this this thing, right? So in terms of bar magnets, if we want to approximate our planet as a bar magnet, this is the South Pole, the real or the true South Pole, and this is the North, the true North Pole. But of course, if you learn geography, we are stuck with the opposite name, right? Okay. So good luck. I'll see you either tomorrow or Wednesday. Good luck.
Thank you.
Thank you.
Thank you. You get the answer, Braden?
Yeah, and it's the answer that I got on the it was the
Okay.
correct one. I just have to practice when to do subtracting and adding. That's all.
Okay. Cool. All right. You should be in a good shape.
For sorry, for the have you put the exam slots for sales up yet?
Oh, I will put all of those later.
Okay. Okay.
Don't worry.
Thank you.
There will be up there.
Okay.
If you have approved accommodation, it will be easier if you don't take it in class because we only have that room for an hour.
Yeah, no, I can't take it in click because the hour and
Yeah.
I've tried that before. I can't do this. Yeah. So
All right. Have a great the rest of your weekend.
okay.
All right.
Thank
Yeah.
you.
Bye bye.
Bye bye.